So now that you learned about identity matrices and inverse matrices, you are ready to solve a matrix equation. We're not ready to jump into solving a system of equations, but this is very much similar to it, so it'll be no problem when we get to there. So let's look at this matrix equation very carefully. I have a matrix, and when I multiply it by some other matrix that I don't know, that's why it's an X, it's an unknown matrix, I get this matrix back out. So this matrix times some unknown matrix, which we'll find, is going to equal that matrix. So if this was a regular algebra problem, and I had some number 2x equals 10, how would you solve this? Well, you would say divide by 2. What you're really doing there is taking the inverse of 2. The inverse of 2 is 1/2, and you're multiplying by the inverse of 2, which is 1/2. This inverse operation, which hopefully you've heard before, undoes that multiplication, and then you have isolated x, and you end up with your answer over here, which is 5. So keep that in mind when you're solving these matrix equations. They're very similar to solving equations that you've seen in the past. But let's look at our matrix equation here and write it down differently. I have a matrix which I will call A, and I'll write it down here. This is matrix A, and we're going to call this matrix B. Well, think about it logically. If I have matrix A times some matrix I don't know, and I get a matrix B out, how do I find out what X is? Well, you need to do the inverse operation. The inverse of a matrix A is the inverse of a matrix A, and you just found those. If I took the inverse matrix, let me write that a little nicer. If I took the inverse matrix A times the original matrix A, I've just undone that multiplication to matrix X. But you also know with algebra that if you do something to one side of the equation, you better be doing it to the other side. And remember, or just keep in mind that the inverse matrix must come first because there is no commutative property, if you recall that from way back. There's no commutative property with matrix multiplication. So look what I've done. I've taken the inverse of matrix A times A. Well, what should happen? The same thing that happened over here. They cancel. They undo each other. They're now gone. And you are left with the matrix X equaling the inverse of matrix A times B. And we can do that algebra. So let's look at this example specifically and follow that general rule. I have matrix A times X, and that will equal matrix B. This is a matrix as well. So the first job is to find the inverse of matrix A. So let's do that off to the side. Find the inverse of matrix A. I'll just do it over here. So A inverse, if you recall, is 1 over the determinant of A. The determinant of A is 3 times 5, which is 15, minus negative 7 times the negative 2, which is 14, which is a very nice number to have for your determinant. And then you rearrange things in your matrix. The 3 and 5 switch positions. The negative 7 and negative 2 will both become positives but stay in their position. And then when you multiply through, well, this is just 1, right? So 1 over 1. This truly right here is your inverse matrix. So we'll use this. I'm going to put a circle around it. This thing right here is your inverse matrix. I guess it's a square. So what did the equation tell us to do? It told us to take the inverse of matrix A times A. Well, if you write this all out, and you're certainly welcome to, you're going to get the identity matrix. And that's just like having a 1 in front of this X. There's always a 1 there. There'll always be a 1 identity matrix in front of that matrix X. So let's actually write it out, and I'll try to color code it. So I have my inverse matrix. Need a little more room. My inverse matrix, 5, 7, 2, and 3, times my matrix A, which is, I'm trying to get my pen to work, is 3, negative 7, negative 2, and 5, times that large matrix X, meaning it's capital letter. All right, and now I'm going to need to take the identity matrix in front of B, which is 5, 7, 2, and 3, and I will multiply that by matrix B, which is -2, 3, 4, and -1. Now this might look scary, but watch what we're doing. These two are inverses of each other, so when I multiply it, they pretty much go away and cancel. And these I'm just going to end up multiplying. A 2 by 2 matrix times a 2 by 2 matrix should not scare you. What this becomes is the identity matrix in front of X, 1, 0, 0, 1, times the large matrix X. And then I'm going to go ahead right away and multiply these two matrices and get my answer matrix. So I will take 5 times a -2, which is a -10, plus 6 is -4. And write that in right here, -4. Then I will do 5 times 4, which is 20, plus a -2, which is 18. And write that in first row, second element. Here I have 7 times a -2, which is a -14, plus 9, which is a -5. And finally, 7 times 4 is 28, plus a -3 is 25. And you're done. This number here, or this identity matrix, you don't really need to write. Just like we don't write a 1 in front of this X, we don't need to write the identity matrix. And so your final answer ends up being that your matrix X that was missing is -4, -5, 18, and 25. That was the unknown matrix that was up here in this problem. Meaning, if I took A, matrix A, times X, this matrix, I would get that one back out. So you could check these. Here's a guided practice problem. I will again walk through it. If you think you've got it, go ahead and work without me. Otherwise, I will start all over and maybe skip some steps that you can skip so you don't feel so overwhelmed with the process. So let's write down what we have here. I have a matrix A times some unknown matrix X, giving me this matrix B, and we need to find out what is X. Well, your rule is to undo that A that is being multiplied by X using inverse operations. Well, that's the inverse matrix. I'm going to multiply both sides by the inverse matrix. I need to find that inverse matrix before I can do that. So the inverse of matrix A is going to be 1 over the determinant of A, which is -24, -24 minus 0. And so we're going to get just -24. That was quick. Then you switch positions around in your matrix and you switch signs. So the -4 and the 6 switch positions, and the 0 and the 1 change signs. Well, 0 can't be positive or negative, so that just stays 0, but you get a -1 up here. Multiply that 1/24 through your matrix, and you will get a -1/4. It's really 6 over 24, and I'm reducing it to 1/4 right away. You get a positive 1 over 24 in this position. 0 here, and 4 divided by 24 is 6, so you get a positive 1/6 there. That is your inverse matrix. So take that inverse matrix, I'll leave it in green, -1/4, 1/24, 0, and 1/6, times the matrix that you had in the original problem, 4, 0, 1, 6, times large X will equal the inverse matrix again, -1/4, 0, 1/24, and 1/6, times matrix B, 8, 9, 24, and 6. And these two matrices in the front, the inverse of A and A, will go away. They become the identity matrix. So X matrix ends up being just the multiplication of these two matrices. Don't be scared. You can do it. Just because there's fractions, we'll do it together and slowly. So I have -1/4 times 8. Well, that's just 8 divided by 4, which is 2. But it's a -2. So I'm going to write that down in the top position. Maybe I'll make this one red. And I can't do this all in my head at once, so I'm going to write that there. But I had 8 times negative 1/4 is a negative 2, plus this right here, 1/24 times 24 is just 1. So this is my element number there. Then over here, you had negative 1/4 times 9 is just negative 9/4. Nothing you can do with that. And then 1/24 times 6 is 1/4. So I'll do that later and get my answer. Down here you have 0 times 8. Phew, that's easy. That's just 0. And then you had 1/6 times 24. So 0 times 8 and 1/6 times 24 is just 4. So 0 plus 4. And then you had 0 times 9, which is 0, plus 1/6 times 6 is just 1. So 0 plus 1. And then you can clean it up and rewrite it. And you get negative 2 plus 1 is a negative 1. Negative 9/4 plus 1/4 is a negative 8/4, and that reduces to negative 2. 0 plus 4 and 0 plus 1. And you have found your missing unknown matrix that belonged in this equation, where you took matrix A times this matrix to get matrix B.